Have you ever just stood and watched rain fall on really dry ground? You know how it just soaks in, like instantly? But then, if the rain keeps coming, puddles start to form. It's something we see all the time, but it's actually a pretty fascinating scientific puzzle. So let's dig in and figure out what's really happening right beneath our feet. So, this is the big mystery we're going to tackle. What's with that dramatic slowdown? It's like the soil has this incredible thirst at first, but then it gets quenched and something just changes, causing all that water to back up. So what is going on there? And look, this isn't just something we imagine. It's a real, measurable thing. This data from a study back in 1973 shows it so clearly. The axis on the left is the infiltration rate, how fast the water is going in, and the bottom axis is time. Just look at how the rate starts off. It's incredibly high, over 30 centimeters an hour. But then, bam, it just plummets within the first 10 or 20 minutes, and then it kind of levels off. This exact pattern is what puzzled scientists for decades. All right, before we go any deeper, let's just make sure we're on the same page with our main term here. When we talk about the infiltration rate, all we mean is how much water is getting into the soil over a certain area in a certain amount of time. You can kind of think of it as the soil's drinking speed. Okay, so one of the first detectives on this case was this really well-known American engineer, a guy named Robert Horton. He was looking at this problem way back in the 1930s, and he came up with what seemed like a very logical, very surface-level explanation. Horton was convinced that the entire secret was just in a really thin layer right at the top of the soil. His theory basically had three parts. First, he said the constant pounding of raindrops actually compacts the surface. Second, as all these tiny clay particles get wet, they literally swell up, which shrinks the little pathways for water. And third, fine materials, little bits of silt and stuff, get washed into the surface pores, and they essentially clog the drain. It all makes a ton of sense, right? And you know what? It was a good theory. These are all things that really do happen. But it wasn't the whole story. In fact, it completely missed the most fundamental reason why infiltration slows down. And the crazy part is, the real answer had actually been discovered decades earlier, but for some reason it just wasn't widely known yet. Yeah, the real breakthrough actually happened much, much earlier, all the way back in 1911. It came from two scientists over in Australia, Heber Green and G.A. Amt. And they weren't just looking at the surface, no. They were looking at the physics of the entire system. This slide just shows the difference perfectly. Over on the left, that's Horton's idea. It's all about what's happening on that top layer. But on the right, that's the Green Amt approach. They thought about the entire column of soil that the water was moving through. They knew the answer wasn't just on the surface. It went much, much deeper. Now, the key to the Green Amt model is this really elegant, simple idea. They imagined the water moving down not as a slow fade from wet to dry, but as a really sharp, distinct line. They called it a wetting front, and it separates the totally saturated soil up top from the dry soil down below. This front is moving down to a depth they called LF. Now, to get why that wetting front slows down, we just need to understand one key concept, the hydraulic gradient. Okay, the easiest way to think about it is like a ball rolling down a hill. If you've got a really steep hill, that creates a strong force, and the ball just flies down, right? But a gentle slope, well, that creates a weak force, and the ball just kind of rolls slowly. The hydraulic gradient is that invisible steepness that's driving the water through the soil. And right here, this is the core of the whole explanation. When the water first hits the soil, that wetting front is super close to the surface. The difference between the water on top and the dry soil just below it is huge. That's a very steep hill. But as that wetting front moves deeper and deeper, the distance gets bigger. The hill gets longer and way less steep. So the driving force, that hydraulic gradient, it gets weaker. And because of that, the water slows down. It's really that simple. And this isn't just a theory. Lab experiments show it perfectly. Just look at this data. The wetting front got down to the 10-centimeter mark in just 3 minutes. But to go the next 10 centimeters, down to the 20-centimeter mark, took a total of 12 minutes. So that second part of the journey took 9 minutes, 3 times as long as the first. This is the Green Ant model playing out right in front of us. Okay, so now we get why infiltration slows down in, a perfect lab setting. But how does this actually apply to a messy, real-world rainstorm? Where the things we really care about are puddles and runoff.
Well, this is where two more engineers, Main and Larson, come into our story. In 1971, they took that awesome green ant model and they adapted it to answer that exact question. They wanted to be able to predict the tipping point, that precise moment when the ground basically says, I'm full, and water starts to pond on the surface. What they figured out is that during a rainstorm, infiltration happens in two totally different phases. At the very beginning, it's supply controlled. This just means the rain isn't falling fast enough to overwhelm the soil's ability to soak it up. The infiltration rate is just whatever the rainfall rate is. But eventually, as the soil's capacity to absorb water drops, the whole system flips to being soil-controlled. Now the rain is coming down faster than the soil can possibly take it, and the soil's own properties become the bottleneck. This graph shows it beautifully. Check out curve number 4, down at the bottom. This is like a light, gentle rain. The rainfall rate is always lower than what the soil could potentially take, so the infiltration rate just stays constant. It's always supply controlled. But now, look at curve number 2. This is a much heavier rain. For a while, the infiltration rate just matches the rainfall rate. That's the flat part of the line. But then, right at that point labeled TP2, the soil's capacity drops below the rate of the rain. That is the exact moment a puddle starts to form. And from that point on, infiltration is soil controlled, and it follows that classic downward curve we saw before.
So we've got these fantastic theories, right? But how do scientists actually go out and measure this stuff in the field to test the models and, make real-world predictions? Well, they use a whole bunch of different tools, and they're all called infiltrometers. I mean, some are as simple as these metal rings they pound into the ground. They fill them with water and then time how fast the level drops. Other devices are more complex and actually simulate rainfall over a small controlled area. All these gadgets are designed to take the principles we've been talking about out of the textbook and measure them in the messy real world.
So the next time you see a puddle starting to form, you'll know what's really going on. It isn't just a sign that it's raining too hard. No, it's the visible result of a hidden battle. A battle between the water falling from the sky and the soil's ever-decreasing ability to pull it downward. A battle that's all being governed by the weakening of an invisible force, that hydraulic gradient, deep within the ground right beneath your feet.